Anyhow, good afternoon. My name is Eric Christopher. This is David Blaikie. We're here to give a little tutorial on how to do debug information for your language. We've both been working on debug info a little too long in LLVM, so it's been an interesting refresher, if nothing else, on how to add it to a new language. So brief introduction here. What is debug info? It's mapping of source to binary, right? You know, program structure, lines, columns, variables. It's used in debuggers, profilers, editors. Side note, I know an editor that uses debug information to power their autocomplete, which is hilarious. So since there's already a tutorial language, I chose the Kaleidoscope language for this, which it's that, right? It's the tutorial there. And basically, it's a little jitting sort of thing, but debugging jitted code doesn't work. Blame Lang, and I think about half of you did earlier. Basically, it takes top-level statements and basically takes definitions, jits them. You know, it looks about like this, where this is your top-level statement. It will be your main for purposes of this discussion, and then you've got a couple of little functions, there's some control flow, there's some variables, there's some stuff, right? So made a few changes to the Kaleidoscope just to power this a little bit, which is I disabled the JIT because it doesn't work and there are some issues with debugging JIT code and Kaleidoscope and stuff. I disabled optimization passes, most of them the first time, and we'll get to that later. And then I removed all the helpful prompts because it's kind of an interactive, you know, REPL kind of language and status and all that kind of stuff, to where I could do this at the end. Yes, I redirected standard error through Clang because it automatically dumped the entire module to standard error. And if you're on a Mac like this, the -G is important at the end. Thank you, dsym-util. So what's Dwarf?
So Dwarf is the international standard. International? Standard, anyway.
It's standard. It is not actually an international ISO standard, no.
For debug information. So it describes how to represent all the stuff that Eric mentioned earlier, variables, types, functions, et cetera, et cetera. It's the interchange format between many consumers and producers. So producers like GCC, Clang, ICC, et cetera, and consumers like GDB, LLDB, profilers, and all of the other fun things. It's fairly general. It talks about all sorts of languages and all sorts of language features, and has guidance about how you might represent particular language features using particular Dwarf features. But it's really just guidelines. So you have to be a little careful about the exact stuff you produce given what your consumer might be expecting. You can end up, if you go to the next slide, so, for example, GDB's acceptance of Dwarf has become, over the years, fairly good at understanding GCC's output. You might step outside that particular path and find yourself with very little support. So you do kind of have to be a little cognizant of that. One of the best examples of this is a bug that Eric didn't really know existed because he was living on Darwin for quite a while and using an old version of GDB and a lovely new version of LLDB. But for a while on Linux, using a nice modern version of GDB, you got some really strange behavior. If you set a breakpoint using a function name, and then you ran your program, you would find that you broke in some other places. More specifically, you broke at the end of the previous function than the one you asked to break at. That was due to this particular feature. The details are not terribly important, other than to say GDB did not behave well when we used this Dwarf feature, and so we don't use it, or we use it in a very constrained way that's compatible with GDB's understanding of the world. So Dwarf has lots and lots of data for lots and lots of different things. Two of the biggest main sections that we'll care about here are debug info, which is essentially just a tree structure, sort of looks like almost XML. You've got tags and attributes. You can describe all sorts of things using those tags and attributes. And debug line, which is the line table, which describes which instructions in the program correspond to which line of source code in your source code. And we have a lovely tool called LLVM dwarf dump. You'll find dwarf dumping in all manner of tools. Darwin has a dumper. Like 3 different object utilities have dumpers. We have a dumper. And it can give you a nice textual representation of all of this stuff. There are some other pieces of debug info that we won't go into great levels of detail about. They're mostly implementation details. If you're looking for the actual information you produced, most of it you'll find in these 2 sections. This is the structure that I was describing earlier. Like I said, looks sort of like XML-ish kind of tags and attributes. Different textual representation, but not terribly important. So you've got strings and numbers and all the other fun things. And then you have a line table. How the line table is implemented for efficiency reasons on disk is a fancy state machine, but in the end, you have addresses, the lines on which those addresses are, and they're just contiguous from the next one to the next, and some flags and other things. That's the basic idea. You want to go into some of this?
Sure. Okay, so DI Builder. Basically, DI Builder is the debug info equivalent of IR Builder. I'm going to assume everyone has at least some general idea of how IR Builder works. You've at least generated some LLVM IR that wasn't by writing text in a file or explicitly calling APIs you probably shouldn't. So DI Builder works just the same way, except it's for building LLVM IR metadata that we use to power all the debug info in the back end. Now, it's very simple. It just takes a module. It's, you can create some compile units, some, subprograms, all sorts of data. And we'll go into, as we go through, how to add some source, everything up through source and variable location information to Kaleidoscope, exactly how to use a lot of the little different functions and what that looks like. So there are some things that you need to keep aware, though. There's some module level setup things that if you don't remember these, you'll end up not having any debug info, or it'll look weird, or it won't work on your system. Like, don't forget to add a module flag with the debug info version, otherwise we strip it out. Given that I approved the patch to add the module flag, you'd thought I'd have remembered that and not spent 10 minutes debugging it, trying to figure out where my debug info went.
And at some point, we should actually add that to the DI builder so you don't make this mistake like we did.
Yep. And then not all targets support all dwarf. So Darwin only supports dwarf 2. Yes, it supports that old version of dwarf a long time ago. Mostly it's that dsym util only supports dwarf 2, and it will mangle anything else that you emit. So for now, for the purposes of this, since I did it on my Mac, everything's going to be in dwarf 2. There are a few different encoding changes, but it's not really that important, right? So dwarf additions for Kaleidoscope. I added a language tag. It's pretty easy. There are a couple little small places you change. If anyone's interested in the diff, it's actually 2 places in LLVM. It's not too bad. There is no vendor range for this, so use it with caution. Most things in Dwarf have a vendor range if you're allowed to change it, which basically means, I'm doing something that's very specific to Apple or Google or Sony or whatever. I'm just going to add my own little vendor-specific Dwarf information. Language tags are not vendor-specific, so be careful or you'll be using the Go or Python or Rust or Swift. I think Swift got in, the Swift language tag. Make sure you don't do that. So first thing you have to do, the big container for everything is the compile unit, right, and debug info. So we're going to first create our debug info builder. I kind of started a little struct to hold some stuff I needed for debug info, in this case, the compile unit. And, made this big global because it's not, great design. And, create the compile unit, right? We've got our language, we've got our source file, which, yes, I hard-coded in. Thank you very much. We have our directory also hard-coded because it takes standard in, right? So it's the Kaleidoscope compiler, and the rest of the stuff you don't need to worry about too much. It's mostly like runtime language stuff that we haven't pulled out completely to optional. So what does this end up looking like? Well, it looks about like that. And where's Duncan? Duncan, I know you're in here. There he is. Duncan's why this isn't very legible anymore. But it's much smaller, so we thank him for it. The most important part to look at is the printout here at the end. The metadata is just references all over the place. Most of these metadata references in the middle are actually temporary metadata that are going to get resolved later. And everything else says we create a compile unit with a language of KS and a file of Fibonacci in the current directory. And ta-da, it looks like this. So we added just a few lines of code, quite literally just a few lines of code, and we actually have at least a compile unit for our little module. So we got pretty far that way, right?
So with this much, if you loaded this program up in a debugger, you would probably see that your debugger at least brought up your source file. Might not do anything with it, but...
Yeah, it will at least pull it up and say, I have a source file, and you can't do much. And yeah. So the next thing we really want to do is we want to add a function, but functions require types, functions require function types, which require the types of every argument and every return value, and it ends up being this long chain of stuff that you end up having to add. But really, we didn't need much because Kaleidoscope has one type, the double type. So we had a little bit of code to create me our basic type. It's called double. It's 64 bits. It's aligned to 64 bits, and it's encoded as a float. It's all, it's all very straightforward. It's next, the next, the next, to keep things going. It looks like this in metadata, which don't worry about the first part. It basically is just a big long string. Yeah. And now we can print out our type for our one variable that will have double, and it all works, and it gives you the size, and you can start possibly seeing how this is going to work in a debugger, right? You've got the name of your types, you've got the encoding, so it might be able to print them out. You've got the byte size. All right, now we just need some functions to encode this in, and this got a lot more complicated all of a sudden. You can tell because we're starting to use a smaller font. Do you want to go through the function type?
No, I think you wrote most of this.
All right. So the first thing we need is we've got our type, we've got our double type. So we need our result, and then for every argument to the function that we ended up adding a little bit of code into Kaleidoscope to say, hey, how many arguments do I have? And you just say, okay, I've got that many doubles, and start creating the entire type array for everything. And then you get a subroutine type. Keep in mind, this isn't the actual subprogram, it's just the type of the subprogram, which tells the debugger how to call and how many arguments you take, and because all the ABI stuff is baked in, right?
As a side note, again, Dwarf talks about lots of different languages. When it says subroutine, it means function or whatever other term you might have for a block of code.
Right. So more code for this because it's not the same. So this is the last bit that you needed to get a subprogram die that doesn't have any actual information other than, well, you'll see what it has. But walking through, you can see we just have the builder here. We're saying, give me a function with my context, which is DI descriptors. It's a big hierarchy. There's documentation. First, we need a file, though, which is a little interesting. But we've already got all that information sitting around because we need it for the compile unit. Why are we duplicating it?
Dwarf and other reasons.
Dwarf and other reasons. So then our name, if you have a linkage name, it would go there. Like for C++, all the mangled names, they kind of go there. The unit, the line number you're at. Here's our function type. We're saying it's internal linkage because, well, it's a little jitted thing. Who cares? It is our definition, though. We are creating the subprogram definition as opposed to a prototype. What line does the scope start at? That's important so that, I don't know if you've ever seen it to where you put a breakpoint on a function and it breaks on the actual function as opposed to the first curly brace, or even worse. Anyways, it's prototyped because we said it was, and some stuff. And this last little bit here at the end, this F, that F is actually the LLVM IR function. That way it has a way of going back and connecting to the LLVM IR. So everything in the metadata actually ends up describing the actual program that's there. the actual IR. All it is sit on top of it and reference bits of the IR and bits of itself as a fully contained whole. So the metadata for a function looks messy. It's got all the subroutine types, the return type, the parameter type, everything like that. But at the end, it's just dwarf. It prints out nicely. It looks like this. Remember, it's Fibonacci. It's the most boring program ever, but it at least has some recursion. And it gives you the file and line where we were started, the types. This type actually turns out to be the return type, which is interesting, but it's not actually showing any arguments yet because we haven't told it that it has any arguments yet, because we haven't added variables yet. Now a quick digression into line information. How many people here have written their own front end? A few of you, right? Did you remember to add source location information to your front end? Excellent. Not all of you raised your hand again. So build source location information into your front end. It's important for more than just diagnostics if you'd like debug information. Build AST and Lexer dumping mechanisms for the same reason. So I'm going to back this out and show you what pretty much Dave did here, because none of that stuff existed in Kaleidoscope. So I'm going to scroll through while you talk it through.
So the first thing I realized was that our tokenizers, so Eric had done a simple prototype for location information, and I realized that even the tokenizer was getting the location wrong. Of course, what it was doing is it was keeping track of the current location as we were reading bytes through the file, which means the current token was before the current location, which was no good. So I started debugging the tokenizer. I added dumping support for the tokenizer, and I started dumping the location. There's a commented outline somewhere where it prints out the location eventually. But anyway, that was the first thing I did. And then I realized, well, actually building the AST had the same problems. We were just, whenever we built an AST node, we'd attach the current location. But say, for example, the if would be built after we'd parsed the then and else blocks. So by the time we actually built the if AST node, we didn't have the location of the if. We had the location of the end of the if. So that was why dumping support was useful. I dumped the Lexer, I wrote the expected dump output, I debugged the Lexer until it had the expected output, and then I dumped the AST and did the same thing. And eventually we had pretty much correct location information. There are still a few bugs in CodeGen, I think, in terms of where we'll describe the location of particular pieces of the generated code, but it's close to right. But it was also probably the most code we had to write for this. It's fairly repetitive, fairly simple code, but it was certainly the most code. Right. You'll see the usual sort of AST kind of repetitive patterns that you'd be familiar with if you've ever written a front end. Right. Or read one, like Clang.
And since it's showing up here on the screen at the moment, so one of the things that we did was wrote a quick routine to say, hey, tell the code generator everywhere we are to emit a location. So I'll go back to what that is in a second, but the emit location should be up here. Whatever. We'll cover it in a minute. But basically, to tell the builder to start attaching line information to all the IR instructions you're generating during CodeGen. So you have to tell, that's the one part where you have to start communicating back to the actual builder and say, hey, I have a location. You need to know where that is, right? So back to here.
Yeah, we'll see some of that when we start to look at the IR of the actual function. It has to be told where each instruction is located so that the line table can be produced correctly.
Right. So we also had to add a few more things here, like lexical blocks, like a function scope map to know what function we're in so that we can tell the line information, all right, we've got some functions, we've got some scoping. All right, what scope are we in when we're in this function? Are we in the function? Are we in something else? Where are we? What are we located in? How deeply nested are we? So we have a little bit of a scope nest there and stuff like that that we added. So what this looks like on the metadata is actually really simple. So this is actually the normal IR first. You're just calling a function. And then it's just a simple metadata tag on the end that references line, column, file inline data later. So we're in function #0, which looks like it was probably fib, at line 6, column 5.
Yes, this is in fib. This is the ret1 function call in fib.
Yep. So it's all pretty simple. Optimizations, one of the things that we've done with the LLVM backend is make sure that the LLVM backend actually knows how to propagate this information. If you start to see your line information disappearing, probably should file a bug at that point because all of the optimizations should know how to propagate the information.
But of course, some optimizations are fundamentally lossy. If we common sub-expression eliminate, well, now we've only got one of those expressions. We can't say that it's at both places where you wrote the code.
So the line information for dwarf starts to add interesting things to your program. This is the kind of information that you actually want to see, you actually want to use, you actually want to play around with. It adds, for example, a high and low PC to your subprogram. So you can say, hey, within this range, I can set a backtrace, and it will go up, and it will figure out what program I'm in based on my PC and everything like that. You'll start to get a frame base, maybe. That's more of the variable locations, just realized that. But you'll start to see locations. And you also get a line table. And this actually is the line table for the finished program here. It's the entire thing. So you can actually see where, with the little bits here, main, which is just our one simple call to fib, calls into here, and all these instructions. So you've got line 4, 5, column 3, column 10, line 6, line 8, all of these things in the statements. We mark the prologue in, we mark the prologue beginning. It's all pretty simple, it's all pretty easy. But remember back here, we didn't have any, I said, frame base, we don't really have any variable information, and you didn't notice anything underneath, because remember, fib took an argument, right? Can't see it. Well, then there's adding variables.
So at this point, even before we've added variables, if you jump into a debugger with this program, you will actually be able to break at fib, and your debugger will stop at the appropriate line. You can step and next. You can go into functions and out of functions. If you, in GDB, for example, type finish, it will finish the function, and it should print out the result, but it doesn't for reasons we'll go into in a little bit.
Right. So then lastly, we're going to add some variables. So I admit I cheated. I only added arguments because my test case didn't actually have any other variables.
The Kaleidoscope language doesn't support arbitrary, local variables. There are a few particular bits where it does, and we didn't bother implementing them.
Right. So there's just a little bit of code that does that because, well, you need to tell your variable what scope it's in. In this case, it's going to be function scope, so that's handy. Again, you need to know what file inline because dwarf. And then we're just creating an argument variable. We say what scope, what number it is, the unit, the line, what type it is, which we already covered. There's one type. And then we insert an actual instruction into the IR that says, hey, I'm building over here. Please actually insert this declare instruction into the IR. So at this, and then set a debug lock on it for reasons of trying to keep things together. So there's a bit more code, though, for it. Dave?
Right, so if you'd just taken the code on the previous slide and you wrote this, what you would find is that if you broke at the beginning of the function and tried to print out the argument parameter, you'd get garbage. If you stepped into the function a little further, you would get exactly the value you expected. And the reason for that is that the debugger didn't know where the prologue ended. And the prologue is like the setup code for the function. So for example, if you look carefully here, you'll notice that we stored the variable in a locker. Standard C calling convention for a double would be putting it in a register, but what we did is as soon as we got inside the function, we allocated some memory, we copied the parameter into some stack memory. There were reasons for that. So that code never executed, but we still described that the variable was located inside that stack slot. So if you break right at the beginning, before you wrote anything into the stack slot, and then in your debugger you try to print it out, you get whatever was there before. That's no good. So we have to tell the debugger, which bit of the beginning of the function is the prologue, so it can skip past that when you break at the beginning of a function. The way we do this is by not ascribing a location to those instructions, and that's just how we communicate to LLVM's backend. These are the instructions in the prologue. They have no real location, so just skip past those and then tell the debugger at the end of that, this is the end of the prologue. You might have seen in the line table there were prologue end attributes. These are derived from that contiguous run of instructions. And so we just hack this up by unsetting the location in the instruction builder, emitting the prologue, and then setting it again so that those instructions come out with no location. So if we go through this, I don't know whether we provide a nice little...
And one more thing. So as a few people well know, remember when I said I removed almost every optimization pass? I forgot one, which was mem to reg. Mem to reg is part of SROA and takes all of our allicas that we were talking about that we copied everything into. We know how to handle perfectly in the back end as far as locations and frame variables and everything, and it stores it into a register. We're pretty good at it, but not perfect, and so I had to disable mem to reg to get this to work too, because at which point it made it optimize debug information, and the locations changed a lot. And it mostly actually worked, but for purposes of this, you probably want to, at least for the first run, disable all of the optimization passes here. So, see? It really does only work well in Allicas. But this is about what it looks like. What you have here is, so you've got your original code gem for your Allica here. We're storing our parameter D into our slightly typoed address for our Allica. And then saying, and this is how we actually communicate to the rest of the back end that, hey, there's a variable here. This is where it started. This is the Allica it's in. This is the reference and metadata to it. So we've got a callback out of the actual, this is LLVM-IR, this is metadata. So we're calling back out of LLVM-IR into the metadata for all of the full description for our argument X, what file it's in, what line it's in, all of that we then have declared up in the program so we can keep track of it, because debug information has ranges of information for where a variable is. It's not just there's this variable, it's in this location, because you can store it to the stack, you can spill it, you can reload it, you can do all these various things, and you need to be able to describe where your variable is at any different time. So the backend has lots of support for being able to do this, and it's growing better and better support. But it takes a lot of little IR calls to keep track of where all the variables are. And so that's basically what things like debug declare, and there's also a debug value that we're not going to go into now that you only really see for optimized debug info, which, going back to this slide, if you start to see debug value, you probably ran mem to reg. So variables with dwarf. So we had our subprogram. Now we've got a frame base, looking pretty good. We've got a high and low PC. And hey, look, we have our formal parameter now that we've dumped out. It has a location, which happens to be the frame register -8. It has a name. It has a decal file and decal line. I like how it keeps changing every time. I think that's probably my fault.
No, that's mostly mine. I was just trying to tidy up the names.
Okay.
Didn't quite tidy them all up.
And it has a type. So you've got your variable. It's got a location. If that location changed, that would actually be a relocation to one of those sections that we were explicitly not talking about today, but we can talk about later. So now we have full variables for all of our arguments. We have full line information. We have line, we have column, we have subprograms, we have a compile unit.
So at this point, if you ran the program, again, the functionality you would have is you can break on the function, you can print out the parameters, you can even call the function in a temporary expression, like you can just say in your GDB p fib3 and get the answer and all of that sort of stuff. Hey, we might even see a live demo.
Yeah, well.
Excitement.
Yeah, so remember how I was saying that I've got that kind of obnoxious compile line? So this is actually what it looks like while I'm working on it. Oh, that's really small, I'm sorry. Let me see if I can get that. Nope, I can't get that bigger and still be able to see it. So ignore the one warning. So I just created an executable file with some debug information here, and we'll use LLVM dwarf dump on it to look at it. So this is actually the full information for all the kaleidoscope stuff. You can see
that this doesn't have syntax highlighting.
You can see that this doesn't have syntax highlighting, yes. As an aside, by the way, running all of this through a web syntax highlighter set to C++ mode actually did all the syntax highlighting for this presentation, oddly enough. But if you walk through it, you can see, we've got our compilation dir, our high and low PCs for everything. This is, actual, honest debug information, including types and locations and A ranges and a full line table and strings and pub names and pub types and everything, right? All the sections we weren't mentioning. Now, if we really wanted to debug it, even using LLDB, so you saw when I set the breakpoint, I even have a line number information, a particular address. I can run. We've stopped. We have the function call with x equals 10, which is what it was, because we've got a source code listing. We've got all of this stuff right now. Can next, which gets us down to our recursive function calls. We can hit next again, which puts us back in fib because this is Fibonacci and it's kind of annoyingly recursive. We can finish, which will get us a return value of that inner call of 34. We can finish again, which gets us 55 and puts us back to the fib of 10, which is our final actual result. And if we really wanted to, I think we can do, call fib of 5? See if that works. Is that the right answer? I think so, right?
Was when I tested it earlier.
Yeah.
At least it's the same answer I got before.
OK, so you can do all of that with just the lines of code we showed you, plus the enormous amount of lines of code of trying to actually figure out how to add source information to a language that didn't have it. So going back to the presentation, we'll talk about a couple more things here.
So this is sort of a detail that you won't necessarily have to worry about in terms of generating debug info, IR, and metadata. It's not a feature of DI Builder. You don't see it anywhere there. But it's something that might be relevant to you if you're debugging the debug information quality of your program or a few other esoteric cases that I'll mention here. Like if, for example, you had your front end generate code that looked like inlining, but wasn't. You didn't want to generate separate functions for it, but you wanted to make it look as though there were function calls for some reason. Or you're actually doing some inlining in LLVM, and you want to make sure you preserve the metadata and properly express the transformation you've performed. So imagine in our little Scratch program how we had that little ret1 function. Obviously, it's a nice, simple function. Why would we belabor the user with actually having to execute a function call? No, of course, LLVM is going to inline that function call. And when it does so, we've just lost some source fidelity. If we just inlined it and you stepped through your program, you'd be very confused by stepping and going to another line and then coming back again. Or you'd look at the backtrace and you'd be like, wait, why am I here? How did I get here? Why am I there when I'm in this other function? So Dwarf has the ability to express describing the fact that these particular instructions in this function actually came from some other function. And so we have to represent that in the LLVM metadata by using that extra fourth flag in the location. Previously, we found that to be null, and now we're actually saying, well, we're really here, but we're here inlined into here. And once we do that, so this is, for example, we inlined the ret1, and so now we just have a direct store. Once we do that, we get a dwarf dump that looks like this. So now inside our fib subprogram, we actually have an inlined subroutine with its address range, which is nested inside the address range of fib, with its call, file, and line. So we can get a nice backtrace. We can say, oh, there was a call to ret1 at this location, even though there wasn't really. There was originally in the source code. and an abstract origin, which allows us to deduplicate all of the other description of the subprogram. We just refer up to the subprogram that actually describes ret1.
So I'll admit that I cheated in one part of this. So remember when I said that I added the DW-Lang KS for Kaleidoscope? Well, it's not actually supported by any debugger, so it had no idea how to call anything or stuff like that. But DW-Lang C is, and well, we were using the C calling convention anyways, the C ABI, so if you happen to have noticed in that compile unit that I actually dumped after compilation, it just said that this was C. So yeah.
So the first time we noticed that was when we had implemented subprograms and we said finish, and it didn't print out the result.
Yeah.
Because it didn't know the calling convention, so it didn't know where the result of that function call was. As soon as we switched the language to C and you said finish, and went finish, the result was 5. And you're like, oh, okay.
So as a note, if you're implementing your own programming language, you might want to tell the debugger how to debug it. I realize that sounds like a simple statement, but didn't do that and was very confused at why I wasn't getting any return values.
Right. So I mean, that's important for all things like calling conventions. Obviously, if the debugger is if you're going to write an expression fib3, it needs to know where to put 3 when it calls your function, and so that could depend on the ABI and everything else, as well as obviously expression evaluation.
Right. Because none of that, unfortunately, is part of Dwarf. Dwarf right now depends on calling convention being known. It has to know based on types, and it infers a lot of information about calling conventions and everything like that. So it's not particularly, it doesn't describe the entire program in that way. It'll describe structure and variables and everything else, but it won't describe that.
And things like evaluating your expression. Do you use a double colon to separate namespaces? Well, that depends on the language. So debugger needs to know what language it is so it can parse your expressions in a meaningful way.
Yep. All right. So questions with the requisite cat picture. Anyone have any question about how to add debug info? Oh no, to Leslie.
So now that we're totally psyched about adding debug info to our little toy languages, where can we find your tutorial?
I will be checking the tutorial in. Because it's based on Kaleidoscope, I will just check it into the rest of the tutorial stuff after a bit. I wanted to get it all done first before checking it into.
Awesome.
Yeah. Nope.
The question was, can we do an OCaml version? The answer was a clear no.
All right. Yep, got one more here.
Is there a standard way to strip unused debug info? Say, I'm generating debug info, some optimization, removing, say, some functions, and I want to remove the metadata attributed to these functions. What is the standard way to do that?
Pray.
So some of that will happen naturally.
Yeah.
Like we already have things like merge func and dead code elimination and all sorts of other things, in which case you will get something like the subprogram you saw first, where you won't have high PC and low PC and anything else, because obviously there's no function. But we're still describing the function for you because that can be useful to an end user of like, well, I wanted to evaluate this expression that I can clearly see in the source code. Well, at least if I can type the expression and my debugger can say, I know that that's a function, but I don't have the code anymore, that's useful to an end user. That's not always the right answer, of course. If this is an inline function that appears in every single source file or multiple CPP files, you might want to drop it entirely along with all of the dwarf. There's no simple mechanism for that. What the metadata looks like when you drop a function is we just drop that function pointer from the metadata record, and then you just don't get the live information, the low PC, high PC, but you get the rest of the description.
Right. It would require a lot more it would require a lot of graph walking to do it otherwise, because, well, remember when I back up here where I was talking about function, like the subprogram, well, first I need to define types. Well, what if your type is only used by that function? And this gets us into the entire notion of what things like comdats were used for originally, which is like, stripping out debug information out of the final executable when you're linking. You only want one version. Well, if this is part of the comdat and nothing in that comdat, you can just discard it. We don't really have that notion in LLVM IR, and metadata definitely doesn't use it. So if you do any optimizations that completely remove functions or completely remove types, you're probably still going to have a type around.
If you taught your optimization to actually remove the subprogram record rather than just nulling out the function pointer, you might actually get
You
most
might,
of it.
if you null out enough things, you might actually get it to drop, but you probably won't.
Yep.
I'm just going to be honest. You probably won't get it to drop.
How well do these techniques that you just showed us interact with tail call elimination?
Everyone wants to know about optimized debug info. I'm shocked. All of these work as well as can be expected with tail call elimination is probably about the best thing I can come up with. Tail call elimination is hard. Remember we were talking about things that are just hard in debug info? That's one of them, right? You come talk to me later about that. We can talk about the whole host of issues involved with tail call elimination, common sub-expression elimination, trying to have two lines be at one location, all that kind of stuff. It's probably better to talk about later. What? Hey, I showed you var tracking. A little bit. We're getting better var tracking. Yes?
There. I wanted to ask sort of about using debug info for actually debugging my compiler. I know we have a debug IR pass that is supposed to rewrite the debug information to reflect the IR file itself.
Sure.
First of all, I've never managed to get that working. Is that actually expected to work?
It worked at one point briefly.
I think we recently found that it had already rutted to the point where it's not functioning. Personally, I use the debugger a lot for the compiler. Usually I debug from like actual C or C++ source code rather than trying to construct particular IR examples. Yes, usually I'm debugging the debug info path though, rather than debugging. Well, if you wanted to generate debug info for the IR, that's because you'd be debugging the IR, not necessarily the compiler, which is another level.
Let me maybe explain that in more detail.
Yeah.
What I would love to be able to do is, starting from a bit of assembly, work backwards to the initial IR I generated, my compiler's intermediate format before I even got to LLVM IR, and then back to the source code of the original program in the source language.
There's a guy who did a decompiler talk at the last LLVM. You should talk to him.
So that's the answer. Okay.
I think maybe your question would be, can you have like multiple source mappings and stuff? I don't think Dwarf actually
No, it
supports
doesn't.
anywhere a way to have like 3 different views of the same code.
Right. At which point you're also talking about interpreting the IR while you're going through it as well, and that's a much more complicated issue. And we'll go back to that JIT-BOF that was earlier today. Yes, sir.
Something of a follow-up to the tail call question. So that's
no.
one optimization, and you talked about optimized debugging. Inlining you touched on for a moment.
We talked very briefly about optimized code because it wasn't part of how to get it in your language, but okay.
Right, but inlining you did mention and touched on it, and kind of suggest that it works really well from optimized debugging, but that sounds like a really difficult problem to me. Does it really work well?
It really does, and Dave can really talk about it.
Yeah, I've spent the last 2 months digging yaks out of inline debug info for no particularly good reason. So it does work fairly well, and one of the reasons for that is that inlining debug information is exposed in a lot more places. We've got the sanitizers, address sanitizer, memory sanitizer, et cetera, that all really love to be able to give you nice backtraces. And to do that, they need inlining information, because they want to give you the backtrace that you wrote, not the backtrace that's produced after inlining. So it's sort of like the one blessed optimization almost. It's the one thing that we probably care about above most others that we get right. So
It's actually the easiest one to get right, too, to be
in
fair.
Kaleidoscope, you said that there's essentially no local variables. But in C,
There
C++,
can be, but you know.
loosely speaking, yeah, but in C, C++, obviously, there are. So you fake up stack frames and the debugger displays it nicely?
Let's see, hold on for 1 second. So,
yeah, so the variables all come through pretty well. The variables are a little bit more tricky, because at that point you're running some optimizations, and all of the caveats about losing variables under optimizations come in. as I say, the sanitizers care about backtraces, so they don't actually care about variables. So you might find that you'll get great stacked frames, but you might not have all your variables.
Right, and one more thing here, if I can go back. If you look at the, like right up here where we're talking about the arg variable, it does actually have the scope. So one of the things when we inline, we've got inline scopes and everything like that. So the variable is actually part of the scope that it was inlined into. So you'll see the scope is still attached to the variable. So it knows as that scope moves, and as the instructions as part of that scope move, that where the variable belongs. Now, the one caveat is, oh, but I completely deleted every instruction in that scope. Well, you've lost your variable because you don't have it anymore, because you optimized it out, right?
And you've lost your inline scope as well, because
And
we
you've
attach
lost
those to instructions, and if we manage to remove all your instructions or like CSE them, or like they somehow end up with another location because we collapse them in some way, there's no history left. There's nothing to describe at that point.
Right. Anything else? Oh, got one in the back.
Okay, so I'm going to ask you about optimized debug info, and I apologize. but
Okay, hold on.
But a slightly different question. So,
Okay,
so
but one second, real
yes.
fast. There is a BOF tomorrow morning about debug info. I would like to state there's a BOF tomorrow morning about debug info.
Very nice.
So all the random questions, okay.
Okay, but sort of as a generic development question. So if I'm writing an IR transformation path,
Yes.
and I intend my IR transformation path to do the best it can at preserving debug info, what's the best way that I can use to test this, aside from trying to run it in some place that I know it triggers and print random stuff from the debugger and see what pops out? Like, is there a more systematic way that I can tell whether stuff has been preserved or not?
Well, you can actually look at and before Dave gets a hold of this, you can actually look at the dwarf dumps for it and check and make sure, like, are you worried about variables going away? Do my variables still show up? You can also, remember how I was talking about, here, where you've got a frame base and a high and low PC, and here where you've got the location. In a lot of optimized code, especially if you're doing any sort of code motion or saving and storing variables or having something in different locations, that will actually be a reference to another section in debug info. And what that means is that it will give you per address range the location of your variable in the source code. If you start doing complicated things like SROA, we have a patch for that needs to be reviewed.
Yeah, I'm not sure that there's any, agreed with all of those things. I'm not sure there's any really nice structured approach as such. Yes, you can go and look at the IR or the dwarf dump or various other things to see whether it looks plausible. Check that the variables are there, check that if you're looking at the IR straight after your optimization, well, check that the instructions that your transformation generated have locations. And those should be derived from whatever instruction your optimization used to inform the creation of new instructions.
Another idea, actually, and this is kind of based on another set of test suite additions that we've got, is you could actually, if you really wanted to, you could set up a debugger test before and after, basically that just runs through the debugger and starts setting breakpoints and printing out variable locations, and you can actually start diffing against that. It's under debug. What was that? That's an example or a tutorial on that's pretty easy.
So yeah, those are essentially scenario tests. Those are like, let's actually take the output of LLVM and run it in a debugger and see what happens.
Right.
Which are valuable and useful. And mostly they're about the over-alignment stuff I was talking about before, making sure that the debugger agrees with the kind of debug info you're producing.
Right.
If it's not that issue, I would much rather see tests up in LLVM, testing the dump, the IR, things like that, where we don't have to go out and actually execute code and run other tools. But it's certainly useful as you're working, right? Like, obviously, I have to do that. Ultimately, I'm like adding new dwarf, and, well, okay, let's see what the debugger does with it. Otherwise, it's no use.
Right. It's a fairly macro test, but you can ask either me or Adrian, hi Adrian, on how to write those tests, and I'll show you where the SVN location of the existing tests are if you're really curious about how to do something like that. There was a question up here. I don't know. Oh, hold on. Yay, more optimized debugging questions.
Yeah, so I'm curious to get your opinion about supporting debug information when you're doing link time optimizations. So now you have two files and one function from one file being inline into another file. So how does all that work with dashing?
It just works.
It just works. All of that works just fine with LTO and everything. Yep.
Some of that you can thank Adrian for, I think.
And Man if she's in here.
Yep. Yes, we will literally produce debug information in two different compile units, and they will reference one to the other. Like you'll have an inline subroutine, and it'll say abstract origin over there. And it works.
One word of warning, this takes massive, massive amounts of memory because metadata is not small, and it's an ongoing work. And you can come to the BOF tomorrow morning and talk about it. Also, we've been in here for more than 45 minutes, so technically we're over now. Or no, we are about ready now.
Yeah, I thought we had the hour, so we've got 7 minutes left.
Okay, we got a few minutes left. Any more questions? No. Sweet. All right. Well, thank you all very much. And if you have any other questions, come up and ask.